So let's continue our discussion on hybridization. So I just, this is just to let you know that there is something fancy happening in some hot topics in solid state or condensed matter physics. So this is about graphene, one layer of carbon. The hottest topics in the past 3 years or so in the whole of physics, not only condensed matter physics, is this kind of bilayer or tri-layer graphene. So this one is about bilayer graphene. Now you can think about, you have one layer like this. On top of it, you have another layer, okay? Now, can you imagine if I trace one layer with respect to the other by 0.5 degree, 1 degree, just a little bit, okay? And that is what I meant by the hottest topic in physics at this time. It is called bilayer graphene, or there is a magic angle. The magic angle is about 1.1 degree. You look at it on the top, if you rotate one layer with respect to the next by 1 degree or so, this is the top view of the pattern. It's not fully understood, but you know, once some experimentalists discover something new, then there are more explanations than one wants to see. One can do a lot of theory about it, but one particularly interesting thing is the following. You see, there seems to be an additional periodic structure on top of the periodicity of a single layer. Now, by that I mean the following. If you look at one layer, there is periodicity, 周期性, 周期性. Now, for example, if you are an electron, if you are living here at this location, you see the same environment as living here, the same environment as living there. So you have a periodic potential energy profile for the electron to live in. You can imagine the Schrödinger equation, kinetic energy plus a potential energy term that is periodic. And this period is about that big, right? Because that point on the two ends, the points on the two ends are equivalent. What happened when you have bilayer is that, now, the hexagonal is that small on this picture, okay? So when you have bilayer and they twist by a certain but small angle, you see an additional structure coming up. So it looks as if there is a new further imposed periodicity once you have this little bit of twisting. It opens up a new field now called, well, physicists like fancy words to sell their field. So it is tristronic. It's electronic, spintronic. Now, the way to tune the property of this bilayer structure is to twist the two layers with respect to one another. That's why you can now Google tristronics, you will see all these kind of things. Now, for example, the fascinating thing is that that could form a superconductor if you trace it by 1.1 degree. So a lot of things is not expected when you understand one layer. I think the leading group is at MIT. Next, we will move on to something that will that help a lot of people earn much money. It is sp3 hybridization. Again, there are many Nobel Prizes. Here, graphene single layer already rewarded Nobel Prizes. And then for this one is earlier Nobel Prizes, understanding CH4 molecule structure, and later on becomes the basic idea of semiconductor physics. I cannot control my mouse. Okay, here. Okay. So, what is sp3? Then is now rather natural. We will invoke carbon 2s orbital, px, py, pz orbitals. We have 1 electrons in each of them. So now the linear combination of atomic orbitals belonging to 1 carbon invoked 4 atomic states. It is the S, 2s, 2px, 2py, 2pz. 4 in, mixed, 4 out. Therefore, we will have C1, if to be consistent with the previous one, I should have written it as psi I, but it's the same thing. So we have 4 sp3 hybridized orbitals out. Now, Mr. Mann asked why it's 1/√3 for sp2. Now I hope that all of you understand why it's 1/√4 for this sp3 hybridized orbitals, because the s will not bias any one of the 4, so it will divide itself evenly. So the remaining thing is to find all these coefficients, 12 of them, using normalized and orthogonal properties among these hybridized orbitals. Without doing all the work, I will tell you the answer. So these are 4 sp3 hybridized orbitals written in one of the many ways. But this way is very popular, especially in solid state physics books. It has a kind of a nice symmetry in its writing. So thereby, in this way, I'm not putting any one of these sp3 hybridized orbitals in a special x, y, or z direction. Instead, using the same argument, if this is non-directional, it is non-directional, this is like a 1, 1, 1 vector. I mean, 1x plus 1y plus 1z. So it is kind of diagonal from the origin diagonally out. And you can play around with this idea. This is like minus, minus, plus, okay? It's minus 1x minus 1y plus 1z. So it's another vector pointing in a different direction. And you can play with the angle between any two of them. And that is the famous angle 109.5 degrees. Okay. And that explained the structure of CH4. CH4 methane is this kind of structure, tetragonal. So carbon in the middle, 4 hydrogen, and this angle between any two, this angle is this 109.5 degrees. After you form the sp3 hybridized, one of them will be something like that. Again, the physics is focusing the electrons in one direction, is highly directional. Thereby, you have highly directional structure in the molecules, so formed. Also, it will spread out the electrons from the carbon, lowering the Coulomb repulsive energy. And that will form a very strong sigma bond with each of the 4 hydrogen atoms. So quantum mechanically, when the bond is strong, it will be pushing much lower, gaining more energy, and so on. Okay, and that is the quantum mechanics of bond forming. So it's the same physics at work, nothing fancy, only we need to involve 4 atomic states from 1 carbon, 1s and 3p. That's why it's called sp3 hybridization. So if you propagate carbon sp3 and then bond with the neighboring carbon, which is also sp3 and so on, that local directionality would propagate into a global periodic structure. And that is another key concept to take on to your solid state physics course if you are going to do it next year. The resulting thing is rather important. So this is the structure, okay? And if all the colors, I mean, this model use two different colors, but if you take the other color also as black, that will be the case of every dot is a carbon atom, and if you stare at it long enough, every carbon is surrounded by 4 other carbons in this tetragonal structure. And if you look at this one, the black ones form a tetragonal. If you look at a black one, you have to do it more inside the structure. You see the other 4 of different colors also form a hexagonal, but inverted. Okay, now this is diamond. You pay a lot of money to buy this structure of carbon, okay, because it's very hard to form. You need some high pressure, probably deep in the earth. Okay, so it formed deep in the earth at extreme conditions. How can we get it on the surface of the earth? We have to wait for our chance, usually volcanic activity. Get something out, okay? And therefore, only occasionally you can find diamonds on the surface of the earth. More often, we will get graphite instead. But more importantly, if these 2 colors of atoms in the model, do you see the model? All right, can you see it? Okay, now if you regard black is 1 atom, 1 kind of atom, this is another kind of atom, then it becomes a very important structure for compound semiconductors. By that I mean, compound means 2 elements forming a semiconductor. For example, the most money-making one, I think, is gallium arsenide. Okay, for example, semiconductor laser, this, the laser reading, the this, things like that. You use a lot of gallium arsenide and indium phosphide in your cell phone, etc. All right. So this sp3 hybridized structure turns out to permeate into a lot of big money-making compounds. So I show you if all the dots are of the same color, it is this side. You have carbon, but the most money-making elements on Earth, everything together in the history of human, is silicon. You have the whole silicon industry. In recent months, there's a shortage of a silicon wafer, the very clean silicon so that you can make chips. And you know, every company, Apple, even the car industry, because there's a lot of computer chips in one car now, so they have to cut their production. Also, germanium is an important semiconductor. They all take on this diamond structure. The basic idea is sp3 hybridized orbitals bonding each other. If the two atoms are of different kinds here, black dot, open dots, then it is this kind of also money-making semiconductor. For example, cadmium telluride, I think it is used to make light vision glasses. Okay, so very dark, you cannot see anything, but in military purposes, if you can see, well, that is very good infrared detector, then you can use it to your advantage. Another very famous Nobel Prize winning structure with this sp3 hybridized structure is gallium nitride. Once upon a time, we have very good green and red materials. I mean, the gap is in the green and red color range so that we can make display on the street, semiconductor display, very bright and so on. But there is one material missing, that is blue. So a Nobel Prize was awarded in 2014 to the discovery. Now this is over-the-counter material, actually. You can call and buy this. It's just so happened that no one worked on it and test the property, but gallium nitride turns out to be a good material with a gap in the blue range. There's a lot of material difficulty, processing difficulty, of course. But now, after this discovery, we have all the colors, thereby now you cross the road, you will see very colorful display, very big one. And now, because we have all the essential ingredients to do semiconductor display. And this is a good, very nice story behind the discovery. Three Japanese, they work on this gallium nitride materials when all the people on in the same field work on other things, work on zinc-based materials. So in 1 year, in the old days, you have hundreds of papers on zinc-based, zinc telluride, that kind of materials, looking for blue emitting materials. Only a few tens of paper, 20, 30 papers a year working on gallium nitride. But following a Japanese tradition, they didn't give up, they just work on their own thing. And then eventually the other side died off because the properties are not good. And then eventually they hit the jackpot and then got the Nobel Prize. So with all these examples, I would like you to appreciate a bit of quantum mechanics, not much, LCA, OMO, Schrödinger equation, a bit of matrix thinking. Take us into a fascinating world of molecules, solids, and material science. You need this in order to be a educated researcher. Even if you do experiments, okay? You don't do it try and error all days long. You have to have some basis in your thinking. And I think quantum mechanics is one of the most important basic trainings. So I would like to end this part with a comment I found fascinating and insightful, but from a very early paper of Dirac. So this is the paper in 1929 by Dirac. Dirac wrote papers by himself. You don't find Dirac and someone, okay? Dirac just a lonely physicist, maybe, but he just writes things by himself, all the papers alone, okay? And Flower actually was his PhD supervisor, but you didn't find papers, say, Dirac and Flower, okay? Now, this one is communicated by him, meaning he submit the paper to Flower and then ask him to, serve as the editor and review it and whether it can be published, okay? So at the end, it was published in the Proceedings of the Royal Society of London, so you can look it up easily. So the title is Quantum Mechanics of Many Electron Systems, a very simple thing, okay? It is a fascinating paper. I think also in this paper, you have this Fermi-Dirac statistics. It is only one small section of the paper, but now it goes into every textbook undergraduate education. Earlier than that, he also worked out the Fermi Golden Rule that we discussed a month ago. So I would like to call your attention to the introduction paragraph. I find this one fascinating. So it was 1929, all right? Schrödinger's work, 1926, January. The general theory of quantum mechanics is now almost complete. Nice, okay? And then the imperfections, there's something's missing, that still remains in connection with exact fitting the theory into relativity ideas. Okay, so he knows there's something missing, but no, he had his Dirac equation already. This gives rise to difficulties only when high-speed particles, relativistic particles, are involved, and therefore of no importance in the consideration of atomic and molecular structure and ordinary chemical reactions. So appreciate that Dirac worried or concerned about the physics of atoms, molecules, and chemical reactions as we are doing now, okay? So not only Dirac equation, QED, things like that. He knows the field very well, in which it is indeed, means the quantum mechanics of that time, usually sufficiently accurate if one neglects relativity, variation of mass and velocity, and assume Coulombic force. That's what we did, okay, between the electrons and the nuclei. So remember, we wrote down the Hamiltonian of a molecule, of an atom, coulombically, all the things coulombically, repulsion, attraction, all the time, okay? And here is the punchline. The underlying physical laws necessary for the mathematical theory. Pay attention to this. I know there's one chemistry major. Sorry about that, okay? Dirac says, not me, okay? The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry, meaning 100% of chemistry, are thus completely known. But what is the practical difficulty remain? The difficulty is only that of exact application of the quantum mechanical laws that leads to equations much more complicated to be solvable. So we can write down the equation, we know the Schrödinger equation, we just can't solve it analytically or exactly. It therefore becomes desirable that approximate practical methods, approximation, we are doing that, okay, appreciate that, of applying quantum mechanics should be developed. And we did that here, which can lead to an explanation of the main features of complex atomic system without too much computation. I think I encourage you to reread this whole paragraph again after class. You have to appreciate Dirac's insight, even up to now. Quantum mechanical computations are routinely being carried out by physicists, chemists, and material scientists. There's a whole field called computational material science. The governing equations are known, mostly Schrödinger equation. Okay, so even now it is penetrating into biological related problems using quantum mechanics. Okay, so I really like this paragraph, especially this very eye-catching word. We know a large part of physics. There's some remaining thing, quantum gravity, no one knows how to do it, but we know the whole of chemistry. Of course, chemistry survived for one whole century, new problems comes out, but the principle is what Dirac was referring to. So this is the last page, take-home message. What we did here is no new physics, but we apply what we have done, okay? We developed some application of quantum mechanics, LCOMO, variational method, matrix, dirty thing 2 by 2 mostly, and you can explain a lot of the world of materials, whether it is atoms, molecules, and solids. And then we don't need to remember binding as an empirical business. Remember, oh, this is covalent, this is ionic, this is single, this is double. No, or is LCO, quantum mechanics, seeking a solution to the Schrödinger equation, and we can put all this on equal footing or under one roof. So we have talked about LCAO forming bonds. The wave function tilt to one side has some ionic character. Not so, we have covalent bonding. And then we have discussed hybridization and introduced many fascinating applications. And then we know the bond order, and then we know single bond, double bond, or even half a bond. And we know what are sigma and pi bond by the symmetry, the distribution of the electrons. And then the delocalization of the electron relevant to metals is the Huckel theory of the pi electrons in benzene. So a little idea that does a lot of work, and I think that is the key point in our course. And I hope that for those of you who will be doing solid state, take all this with you into your solid state physics course. You don't need to learn it again and again, okay? Simple bonding. So for next few minutes, I would like to introduce what we are going to do next. The remaining 1/3 of molecular physics has to do with the nuclei motion, but I already showed you the big picture up front. At this point, we know bonding, and therefore we have this bond binding curve. And now, if we sit here, this is the value of energy at the equilibrium separation. But remember, this is the separation between two atoms, A and B. About this equilibrium separation, the two nuclei could vibrate. That will be an oscillator problem, one-dimensional oscillator problem, back and forth around here. That will give us vibrational energy, like an oscillator. And also, imagining this R0 to be a rock of constant separation, this diatomic molecule would rotate in any way with a fixed distance, okay? This is a rigid rotator or rigid rotor problem. You have solved it in your term 1 course. It will give us rotational energy levels. If we add all this thing together, that will be the total energy allowed for a molecule. So it has the minimum energy here, and depending on which rotational level it is in and which vibrational level it is in, it has a certain energy. Transitions between such allowed energies of the whole molecule will give us signals called molecular spectrum. If the transitions are only between rotational level, that means n is the same, no transition between different n's, you will get pure rotation spectrum, rotational spectrum of molecule. That will be useful to get the bond length. From the data, you can get R0. If the transition is between different vibrational states as well as different rotational states, that will happen in the infrared range. It will tell us something about omega as well. Remember, omega is spring constant divided by the reduced mass of the two nuclei square root. Thereby, vibrational information will give us the spring constant, which is a representation of how strong that bond is. So, last word of today, rotational spectrum will tell us the bond length as well as the bond strength. Okay, so that is what we will discuss on Thursday. So we will try to finish up this part on Thursday. Then the last week, I will see what else I can tell you about applying simple quantum mechanics in understanding the whole world. All right. So I will stop here today. If you haven't done your course evaluation on site, please do so within today. The link is still active. All right. So long. I will stay here if you have questions.